All right, so we're working on number 3 here. The pusher is easy. Part A is easy, and everybody gets this. Because, of course, work of the pusher equals force of the pusher times distance. Simple. You're given the force, the 175. So, and we could say, this is where the cosine theta does come in handy. So if the force of the pusher is being applied parallel to the incline and up the incline, then the angle between the motion of the object and the force of the pusher is what? 0. Cosine of 0 is 1. Okay, cool. We're gonna use that again in part B. So work of the pusher equals 175 newtons. We could say cosine 0 if we want, if we really felt crazy, times the distance, which is 6.0 meters. Okay, what do we get? And we've got 3 sig figs, we can leave it alone, 1,050 joules. Lots of people got that part. The larger question is, what about the work done on the crate by gravity? Is gravity doing any work on the crate? So here's where the whole work is only done if the object moves thing gets a little weird. Is gravity acting on this crate on an axis on which the work is occurring, or on which the motion is occurring? Yeah, because the object's going up the crate. Let's look at our line for gravity. Let me expand this. There's my force of gravity, which means I have a force of gravity on the y. Oh, look at that. I have a force of gravity on the x, which is working in opposition to the motion of the crate. Essentially, you know, if the pusher was applying that 175 newtons upslope in a frictionless or in a gravity-free environment, more work would be done, the thing would move faster, it would move farther for the same amount of force. Gravity is impeding its motion. So the work done by gravity, part B, and this is where subscripts come in handy, work of gravity equals force of gravity, and I'm going to note on the x, because it's only the force of gravity on the axis where the motion is occurring. Now, here's where the cosine theta comes in. What's the angle between the force of gravity and the motion of the object? They're opposites. 180. It's 180 degrees. So times cosine, well, we'll say cosine theta here, times the distance. So in this case, well, that would be mg sine 15. So I'll call that sine theta, or that's theta 1, sine theta 1. I'm going to shrink this a little bit. Times cosine of 180 degrees times the distance which this object is pushed. Question. Absolutely. So the angle here we know is that. If we expand that angle, now we have that right triangle, or we have that 90-degree angle. Expand that angle, you still see the angle, right? A flat line in the opposite direction is 180 degrees. So gravity is working on this object down the slope. It's working on the object 180 degrees from the direction that the pusher is pushing the object up the slope. This becomes important because it gives you, what's the cosine of 180? You might have it memorized, you might have to plug it in. -1. Oh, wait a minute. This gives me a sine. I just need a sine! There, you got one. Okay, so we get negative 350.384, etc. If you didn't have the negative sign, I assigned that a half, because I wanted this to be an opportunity to talk about negative work. Can you do negative work on an object? Yes. You do negative work on an object when you slow it down or impede its motion. So if I have an object moving towards me and I push on it, I'm doing negative work on it. If an object, so we can do negative work on an object. In a situation like this, and we're going to actually do one here. I thought there was one in the book. We're gonna do one together where we look at work done by multiple components on an object. Basically, no matter what the book says, and this is, some physics prof somewhere can come along and correct me. One of you, please go major in physics and come back in a few years and tell me that I'm full of it, and fix what I'm doing. I've had students do that before, and I actually really appreciate it. Somebody in this room is related to a student who did that, and I appreciate it deeply. So the point of that whole little diversion there was that the only place I use that cosine theta is when I'm looking at whether the force that I'm talking about is 0 degrees from the motion, so in the same direction, or 180 from the motion. Beyond that, I use a free body diagram to figure out which component of that force is on the same axis as the motion. So I'm doing all that by hand, because that could be sine, that could be cosine, that could be whatever. That cosine theta, FD cosine theta equals work, I'm only using with either 0 or 180, because that gives you your positive or negative sign. Does that make sense? Okay. Let's do a tricky one. So we got a little person pushing a giant crate up a hill. We'll say this is 25.0 degrees incline. Mass of the crate is, nobody's got a numbered jersey on. Okay, 72.0 kilograms. Person looks awfully small to be pushing such a crate. Pushing force, they are exerting, I'm just making up numbers, so this could go badly. Oh, yeah, let's let this go badly, because that'll illustrate a point that I want to get to. Okay, so I'm going to make up a random number. Force of the pusher is 215 newtons. I have no idea how this is going to turn out. So these are always fun. Coefficient of friction between the surface and the object is, we're just going to make up numbers. This is going to be so much fun. Still nobody with a numbered jersey on. When's your birthday, Matt?
6/26.
Perfect. 0.626. That's a pretty high coefficient of friction. What can we determine from this? So let's look at a couple different things. So A, work done by the pusher. B, work done by gravity. C, what force is left? Friction. Work done by friction. Ooh. Now, why am I not talking about the work done by the surface, like normal force? Is there work being done on the y-axis?
Oh,
No, exactly. It is neither levitating nor sinking through the platform, therefore there is no work being done on the y-axis.
yeah, or there's the thing, like the angle could be considered 90 degrees and cosine of 90 is 0.
Yeah, we can do that. We can do that, exactly. Yeah, hey, that's good. I like that. Have I ever talked about that before? Good, okay. So for those of you who missed the 3 cognitive leaps that just happened up here, nice job. We'll give you a star on your forehead. If we think about the force being applied on the y-axis, it's 90 degrees from the motion of the object. Cosine of 90 is 0. There's no work because the force on the y-axis is 90 degrees from the motion of the object. Therefore, you get a big multiplier of 0, so no work on the y. Or we can just say it's not moving on the y, so there's no work being done, which is the simple sort of boil down. Okay. Oh, let's go. Can we do, which one of these can we do without any further calculations, without having to figure anything out? A. So part A, work of the pusher equals force of the pusher times cosine theta, and I'm going to put my little asterisk here, where theta equals, where theta equals angle between force and movement. Oh, and I forgot to give us the distance that it moves. So we'll say that this thing moves 4.0 meters, and we're assuming it's moving at constant velocity. Lots of assumptions here. So F of the pusher cosine theta times the distance that it moves. So work of the pusher equals 215 newtons. What's the angle between the pusher's force and the motion? 0. It's going the direction this person is pushing. Cosine of 0 times 4 meters. What do we get? Okay, so work done by the pusher is 860 joules, and work is a vector quantity, so we're going to say upslope. You don't have to put an angle in here, but you should probably say upslope, or you can let your negative and positive sign serve as proxies, but it's good to just recognize that so that you don't mess that up. So work being done by the pusher is 860 up the slope. Now let's figure out that work done by gravity, and I'll set that aside. Okay, part B. Work done by gravity equals force of gravity on what axis? On the x. These are not to scale. FGX. So force of gravity on the x times cosine theta, again, where theta is the angle between the force and the movement, times the distance the object moves. So work done by gravity then equals mass gravity sine 25. What's the angle between the motion and the force of gravity on the x? 180. Cosine 180 times 4.0 meters. So we have an answer. Now I have a question for you. Is this poor little person actually pushing this thing up the slope? Well, it's pushing them down. So in fact, the box is doing work on the pusher, and we could do that too. Because the work being done by gravity is greater than the work being done by the pusher, gravity wins. This little person is getting shoved backwards down the slope by this gigantic box. So now let's do part C, because this changes everything. So the thing I want you to think about in looking at my free body diagram, because you're not done with free body diagrams in this chapter, draw the frictional force in on your free body diagram. I'll pause this. Yeah, good conversation. So somebody said, well, then shouldn't we change the arrow on the movement? Yeah, we should, and I'm going to get rid of the signs on this, and now I'm going to say that the work being done by the pusher is still upslope, but the work being done by gravity is downslope. So I'm going to lose that negative, and I'm just going to talk about up and down slope. So since we know that the work being done by gravity is greater than that being done by the pusher, and therefore the motion is going to be downslope, where's the frictional force? Friction opposes motion. You have to look at the gravity and the pusher force before you know which way this thing is moving. Once you know which way this thing is moving, you can assign the frictional force. The frictional force is actually going to be upslope. Wait a second. Which is freaky and weird. How do we get the work done by frictional force? What's required here? Oh, Lord Moser, it's a Friday and it's raining. I thought we were done with free body or with sum of forces. Yes. It's a sum of forces. Got to do sum of forces to find the force of kinetic friction. So sum of forces on the x. We said this is moving at constant velocity. We're making that assumption. So sum of forces on the x is equal then to force of gravity on the x minus force of the pusher minus force of kinetic friction. What a pain in the tuchus, because I just gave you the mu k. Oh, this problem is going to be a giant mess. Mu k equals fk over fn. So mu k fn equals fk. How do I get my fn? Oh, I have to do another sum of forces. Equals 0 equals fn minus fg. Fn equals mass gravity. So, oops, what do we have? Mu k mg equals fk. Did I screw something up? Oh gosh, yeah, I totally screwed that up. Thanks. Yeah, it'd be fgy. Thanks. I got all carried away and forgot I wasn't on a flat surface. Mg cosine theta. Mg cosine theta. Okay, so mg cosine theta equals fk. Whew, that was a lot. What are we left with? Well, let's see. We're interested in fk, so we want to solve for that. So fk. Oh, no, we want to solve for that, and we have everything else. Never mind, I didn't need to do all that. You're grinning, Colin, because you knew that like 4 steps back, didn't you? You're allowed to speak up. Okay, so fk equals mg sine theta minus fp. I'm glad you entertain yourself by just letting me go on, Colin. Thanks a lot. Okay, so we've got fk, and the work done by the force of kinetic friction equals fk cosine. Well, friction's always going to be cosine 180 because friction is always in the opposite direction of the motion. Friction opposes motion, period. So fk cosine 180 d, and that's all we need. We can either plug the whole expression for fk in, or we can solve it. It's, you know, I've beaten you with the stick of doing your substitutions. Gee, I'd love it if you did that. I can't make you do that, but I'm going to, because it's just the way I roll. Okay, so I'm getting a work done by kinetic friction of 826 joules. Now, here's where, and again, don't forget. Oh, what did I do wrong then? Yeah, scratch that answer that I just put up there because that was all wrong. I did something wrong. 334.01 blah, blah, blah joules. We got a negative answer because it is working in opposition to the motion of the object. And I got rid of all the signs. We know it's upslope, so I'm going to get rid of the negative and just say 334 joules worth of work upslope. Now, I made up all these numbers. I pulled them out of thin air and Matt's birthday. So, you know, could I write a problem that shows something really bizarre happening, like the box isn't moving? Yeah, let's not even go there. But when you've got like an applied force up a slope and gravity, it does always pay to look at the relationship between those two things right off and decide if it's going to move up or down. Question, comment. Did I screw something up? Okay, so the question, and it's a good question. So if we find out that gravity's winning, essentially, do we then call gravity a positive? Usually what we do in those circumstances is, and this is where physics is not as married to algebraic signs as math is. Physics is more applied. So the sort of practical answer is we ditch the sign, we talk about the magnitude of the work, and we describe it in real world terms, like up the slope, down the slope. I think I've told you my joke making fun of physicists, mathematicians, and engineers, right? Yeah. Okay. So this is where the physicists and the engineers go, it doesn't matter what sign you got, how's the thing moving? Where the mathematicians are all hung up on the signs being perfect. And I think I used to fall more into, like, I thought that it should all work that way, and I understand more now. Like, you got to think about the magnitude of the force or the work and how the thing is moving. So, questions, comments, concerns? Okay. All right. We'll can it for there, and we'll talk about kinetic energy on Monday.